The topic of discussion for today is the properties of gases. So here, the properties of gases that are explained by standard laws. With the help of these laws, ideal gas equation is derived. So the ideal gas laws are nothing but from the Boyle's law, Charles' law as well as Avogadro's law. So what is the Boyle's law? So Boyle's law states that PV is equal to constant, and Charles' law gives us the formula V by T is equal to constant, and Avogadro's law shows us V by N is equal to constant, where P is the pressure, V is the volume, N is the number of moles, and T is the temperature. And with all these three formulas, the ideal gas equation can be derived, that is PV is equal to nRT. R is equal to the universal gas constant, that is 0.08206. Unlike liquids, gases expand to fill the volume available to them, and the volume occupied by the given number of gas molecules at a given temperature and pressure is the same regardless of the composition of the gas. And if you see the partial pressure, the pressure exerted by one gas in a mixture of non-reactive gases and its partial pressure and is equal to that of the total pressure times the fraction of the total amount of gas it represents. Which is, here the partial pressure of gas can be calculated by the formula, that is atmospheric pressure versus the fractional gas concentration. And the next is Dalton's law of partial pressures. So the Dalton's law, which is also called as the Dalton's law of partial pressures, which states that in a mixture of non-reacting gases, the total pressure exerted is equal to that of the sum of the partial pressures of the individual gases. So here, the calculation of the partial pressure of atmospheric gases and various parts of the respiratory system can be explained over here. So the composition of the dry air is 20.98% of oxygen and 0.04% of carbon dioxide and 78.06% of nitrogen, and approximately 0.92 other inert constituents such as argon and helium. And the barometric pressure that can be expressed as PB at sea level is 760 millimeters of mercury, which is 1 atmosphere. So the partial pressure, which is indicated by the symbol P. So the partial pressure of oxygen, that is PO2, in the dry air is therefore 0.21 versus 760 millimeters of mercury or 160 mm of Hg at sea level. And PN2, that is partial pressure of nitrogen and the other inert gases, is 0.79 into 760, which is 600 millimeters of mercury, and the partial pressure of carbon dioxide is 0.0004 into 760, which is equal to 0.3 millimeters of mercury. So these are the partial pressure of different gases in the air. The water vapor in the air in most climates reduces these percentages, and therefore the partial pressures are reduced to a lesser extent, and the air equilibrated with water and is saturated with water vapor, and inspired air is saturated by the time it reaches lungs. So if we see the partial pressure of water vapor at body temperature, that is 37 degrees centigrade, is 47 mm of mercury. Therefore, the partial pressures at the sea level of other gases in the air reaching the lungs are partial pressure of oxygen, that is approximately 160 millimeters of mercury. It is ranging from 150 to 160. And the partial pressure of carbon dioxide is 0.3. And the partial pressure of nitrogen is 563 millimeters of mercury. So if you see the partial pressure of oxygen in the dry air is 160 millimeters of mercury, and with water vapor is 150 mm of Hg. And if you see the partial pressure of carbon dioxide in the dry air is 0.3 millimeters of mercury, and it is same with the water vapor. And if you see the partial pressure of nitrogen as well as other inert gases, in the dry air it is 600 millimeters of mercury, and there will be a drop with the water vapor, that is 563 mm of mercury. So the partial pressure of water, nothing is in the dry air, and it is 47 millimeters of mercury with water vapor. Here you can see the image showing the partial pressures of various gases in inspired air, alveoli and expired air respectively, and the values are given in millimeters of mercury.